Hello, today we're going to learn some HECRAS. So let's start with downloading and installing the software. Once you type HECRAS on your Google, it shows you the links for download and actually the official website for HECRAS. So let's go to that one. It's created by U.S. Army Corps of Engineers. It stands for Hydrologic Engineering Center. That's the HEC part. And RAS is the river analysis system. So that's why they call it HEC-RAS. And this web page shows you all the model capabilities. This is the HEC-RAS main window. You have geometric data window. You can use RAS mapper to create flooding maps, which we love the most. And just an overview, a summary of things here. And here you have a link for download. Of course, it's suggested you go over all these tabs to see what's new and all the documentation for the basically user manuals and everything. But for today, we're just going to do a quick introduction, so get you all up to speed with using HECRAS. So going to downloads, you can see all the versions available. So for Windows, 6.1 is the most current as of today, and I'm going to download this right here. If you're using other machines like Linux, you have that version, and also you have access to all previous versions of HECRAS. If you deliver the project, maybe you deliver a project today to your client, and 3 years later, there is something they want you to rerun and modify. And at that time, HECRAS version 8.2 is current. So you don't need to worry about that. You can always come to our archived versions and install the one that you used back in the time. So I have already downloaded this on my desktop. It's right here, HECRAS. So that's the executable file, over 300 megabytes, and I installed it. It takes less than a minute for you to install. So I'm going to open the software and show you some important things. So that's HECRAS main menu. It's rather a small window. Everything is inside this, like the geometric data window, data for steady flow or unsteady flow, sediment data, water quality data, and run and analyzing it. So to explain things step by step, let me first show you what comes with HECRAS. What comes with HECRAS is basically, if you go open, in your document folder, there is a subfolder called HEC data once you install HECRAS. So here you have HECRAS. If there are other versions of HEC software like HEC HMS, for example, you would see another folder here. But for today, we're only doing HECRAS. And then you will see example data, a bunch of example data for water quality, sediment, 1D, 2D modeling is here. Steady flow is the most straightforward one. So we start with that. And you can model different things. You can model a culvert, but the manual chapter 4 has a very basic example. We're going to show you that. So now everything is populated. Once I open that file, you can see the project is saved, of course, under the document folder, and you have 3 more things: plan, geometry, and steady flow. So let me show you that one by one. Plan is basically a combination of your channel geometry and your flow data. So if you want to run this, you will see your plan is called existing condition. That's also listed here, existing condition run. And there's a short ID. It's a combination of this geometry, base geometry, and event that have a 1, 2, and 10% chance of occurrence. So of course, you can have multiple geometry files in same project, and then you can define a plan to link those. So that's for the plan, basically what geometry file and steady flow file should go into the model. And then geometry is this window, geometry data. So it shows you a plan view of your river system. You see there are 2 reaches upstream, Fall River, Butte Creek, and then they have a confluence at this point. Sutter, and then after that you have a downstream fall river. So each segment you can have their cross sections. Cross sections, you see, it's or sort of a natural channel with a semi-trapezoidal shape, but you can see here there are different stations. So I'm going towards downstream. I can have the other window shown so you can see how I move. So I can go down. So now I'm moving downstream, and then you can see there is another channel cross section. And for each cross section, you would define what's the reach length from here to the next downstream, 500, and make sure you are understanding the units that you have in this model, which is feet. 500 feet, you need to define your channel, main channel, which is this part, main channel roughness. Also, you have left overbank. This is your left overbank, and this is right overbank in your floodplain. And basically, you define all these in the model. I'm just giving you an overview what goes to each menu. So in here, you have your basically geometry. You can add different things to it, culvert, bridge, etc. You can make this a storage area, 2D modeling, and all advanced stuff we don't want to do in this very first example. So that's for geometry, base geometry data. Next is the flow data. So here you can have basically your return periods. You have 10-year, 50-year, 100-year, which are very typical data for running hydraulic models. And as you can see, you can simultaneously run the model with the three. You don't need to make this change and save as a new file and run again. So here the model allows you to run 32,000 simulations simultaneously. That's really wonderful for that. And you can see each portion. You need to define the Q for that, and the unit here is CFS. So for example, your upper reach has a 10-year of 500 CFS, and the other tributary giving you 100. So what goes to lower reach is 600. You need to define that. And if you have another tributary that could increase your flow, you would show that number here. So basically that's for that. And then you have, you can run. This is for run. The guy is running. So you explain in your plan what geometry and what steady flow you want to run. You can change these, have different plans without copy pasting your model. So then you can compute to get some results. So this is done. And of course, you can see the result in terms of cross sections. So now you can see how much water exists. This is your 10-year. You can have different plans showing. So I'm going downstream. You can see how things change. This is the fall river lower reach. You can, of course, run it for the upper reach if you would like, and see how this might not be the best way to see it. Of course, for flooding, you can understand, but if you want to have an idea of the whole model, the profile view is a better fit. So profile view, now I'm showing upper reach. Let me change it to lower reach. Now you can see at each cross section what is the depth of water and how it is changing. So let me have upper reach and lower reach showing together. For 10-year, you can see how your water surface changes. The green dashed line is your energy grade line. So you're basically adding velocity head to the water depth. And then you can see how your slope is basically getting more flat as you move forward to downstream direction. So that's profile view. And you can have also a 3D view of things. So this is actually, in some situations, the most helpful one, because at the same time, you can rotate, you can see how your channel, and then you can play around with the view. So now I'm getting a top view from most upstream towards downstream. You can see if flooding happens in any locations and basically play around with that. And of course, you can get a bunch of tables in data table for data in form of tables, always helpful. In each reach, you can see what's your fruit number, what's your top width, all the hydraulic characteristics that you're interested in. So that's your comprehensive table right here. And then you can also get a concise version of the table. So that is for that. And then always you have your documentation. So let me go over to the documentation part. Documentation, these are also saved on the same folder that is installed on your computer. User's manual is always a good thing to start, an application guide and everything. So for the user's manual, this is where basically showing you all the good stuff for the system that you're using. You know, basically how to use each screen, each window, how to run, how to play around with the table that I showed you. So that's basically for user manual, is a very advanced version of, I can say it's over 700 pages. 700 pages of how to use each button and each window in HECRAS. And another important tool here for you is basically the application guide could be helpful. And then also each specific document for like mud and debris flow, hydraulic reference manual is the one that you would use for the equations. So this is basically an advanced version of just what I just showed you. And these are all helpful. So for this one, for example, we are working with all the equations that goes into this. So let's see, all these equations, transitions and everything in the channel, all, you know, everything that goes to the HECRAS for energy, for loss and things like that. So this is your reference manual of how the model is solving things that you want. So that's basically the one that you should be aware if you're using for a project, for a thesis, for a consulting project and everything. All right, before taking you to all the details of how to create a new file, I would like to first show you a professionally created HECRAS model so you can understand what is expected for each buttons and menus in the model. So this is what has been done for somewhere in San Diego. Some warnings, these are mostly because of different versions, but basically you can see, of course, you have a project folder. It shows you the direction. You have a plan. A plan is basically a combination of a geometry and a steady flow. So you don't have to copy paste your model several times if you want to test different alternatives. You can basically make a change in your geometry and create another plan, like a plan 7.0 here, and just run the model inside the same project folder that you have. So that's a very good thing for model management. For geometry is this button. So here I'm showing you an example of geometry being fed by ArcGIS data. By GIS data, you can see the DEM. So each line here is a cross-section line. You can edit this cross-section, you can plot it, you can do different things with it. And there is a blue line with this arrow is your main river line. So just your main river line has a direction like this. It actually goes upstream a little bit and goes downstream. You can see different cross sections. So if I start with this one, then you can see that's a detailed model, it also includes sediment. This is your sediment field. And you can see the gray line is the terrain data, but then the model is being fed by actual trapezoidal channel information. These are edited manually. And you can see, so you have a list of cross sections. Your most upstream cross section, usually the system that they use, the largest number is all based on a downstream reference. So your most downstream point is the lowest number. And here you have 415. You can go towards the downstream. You can see this number is being decreased, the river station. And basically you have a culvert here. You want to see if this culvert is flooded or not, and then the model is able to simultaneously run different scenarios. So that's why you see this blue line, this blue line. Each blue line is, this is for 10-year flood, this is for 100-year flood. So you can see if I go back to the profile view of this river line, you can see that in this scenario, which is my 2-year, even in 2-year, the culvert is flooded. So that's because you have lots of sediment in this example. So basically just some definitions here. You can press a shift so you can pan this. If you press control, this changes to ruler so you can measure things. Can measure the length. It also shows you dy over dx, or your basically ground slope. And basically key definitions here is that you have a main river line. It should show this arrow in the right direction, and you have a set of cross-section lines. These green lines, these are your cross sections. So this is a pond. And when I get to the pond, you can see that's now, it's looking more of a pond now. And there is a high hill here and everything like that. So that's the stuff goes to your geometry window. River reach, you can draw it with this. Cross-section window is the one that I have here. Here you also need to put your Manning's roughness coefficients and everything. And it works with a set of station elevation information. So you have this station 0. So at 0, your elevation is 12. It goes down. You can see when I'm here, it's a station 11. So somewhere here, and then it gets to elevation 6.9, and it increases again. So that's basically a very big data set of station elevation for each cross section. And another thing goes to each model based next to geometry is your flow data. You can simultaneously run your model for 2-year, 5-year, all the way to 100-year. The model does require to have some boundary conditions. So in this example, because there is a measurement in the field, we do know the water surface elevation at downstream to use it as a boundary condition. And we can of course run the model in unsteady with sediment, with water quality, but here is your run window. And you can run with different combination of geometry file, which I showed you, and the steady flow file. Of course, you might want to have different scenarios if you have the rehabilitation. So what happens if you take all the vegetation out and run that? And there is no need to copy paste this model. You can have all this. Like, for example, if I show that geometry, now that the rehab version, basically now I'm dealing with cross sections that don't have sediment anymore. And because the sediment is removed in this rehab version, then when I plot the profile, then the water surface is showing a little bit lower. I need to rerun this to update this result, but just giving you some ideas. Basically, I'm editing the geometry file and running it again inside the same model. So just going over what you expect to have. For elementary use of HECRAS, you basically work with geometry, flow data, and you run your model all in steady condition. Everything else is advanced application. And of course, you can have a profile view of your water surface and your cross sections, what's happening in each cross section. So let's do all these in a very basic model and go step by step. Lastly, before I start that, I wanted to show you these two tables. They can be very helpful. Instead of graphs that show depth, you can get the actual number. It gives you all the things that you've learned in this course: velocity, top width, fruit number, everything. And yeah, let's do that. So I'm going to start a new file, a very basic file, just to learn HECRAS. New project. Do you want to save? No. And desktop, I have another test folder here. I want to call this test 2. So then I do OK. Again, US customer is good. And now the next thing to work with is the geometry. So geometry, let me maximize this. Of course, you need to have a river reach. It needs to show in the right direction. So one click and double click. I want to have only 2 stations. And I call this my river, and this is my reach. So river 1, reach 1. And okay. So yes, this is the direction I'm expecting. I need to add cross section. So this is not tied to any GIS data, to just keep it simple. So things that you show, it shows you here, it's not really georeference, it's not into the scale, but you're going to import the actual dimensions manually. So now that you have that, you can just have a cross section, and it's showing you the reach you're dealing with. You want to add new one, add a new cross section. Big numbers are upstream numbers always. So you have station 100, and station 100, let me draw something like this: some overbank, rectangular in the middle, another overbank. So station 0, I want to have, let's say, elevation 13. Then I have 5 feet for overbank, and then now 1 foot drop in the elevation. At this same station, I have now a vertical line because I'm in the rectangular channel board. So 9. Then I want to go to the right a little bit for, let's say, 5 feet. So my bottom width is 10, and the same elevation. Now I want to turn up for same height that I had, and that's going to be 10 and 12. And lastly, I want to have some overbank. So 15 for a station, and then let's rise it to 13 again. So you can see some overbank, main channel, another overbank. And then reach length, let's say we have 100 feet of length for all sides. The reason that the model asks you different numbers is because if there is a bend, right overbank might be smaller than left, but that's not the case here. And of course, for left overbank, you might have a rough number, maybe 0.1, but for the main channel, let's keep it as the famous number of 0.015. So I'm applying it. It's going to show everything at 0.1 because I haven't yet defined the boundary of overbank and main channel. Main channel bank station, left bank is my 5, right bank is my 10, and apply. So now you can see these red dots. Red dots shows the boundary. You can leave the contraction expansion coefficients as default. So that's one of your cross section at upstream. You want to replicate this figure at downstream. And now, basically, we want to create another one, add a new cross section, and let's call this one number 1 because that's very close to my downstream. And just 1 foot. We don't really care beyond that. You can leave these, and then you need to draw a shape again. To do that, at 0, I need to go back to my up. Let me apply this. I need to go back up. I have 0, 13. So let's reduce everything by 2 feet maybe. 0, 11. And now 5 feet, 10, 5 feet, 7. Now let's add another 5 to the station. So go to the other side, then 7, then at this location, I want to rise up 10, 10. And lastly, I want to go 5 feet away, 5 feet away, and increase it to 11. Apply it. So this shape appears again, but I need to define the boundary lines. So you have overbank and main channel. So again, 5, and here is 10 for the boundary of main channel and overbank. So apply it, and then it shows in the right way. So basically, it appears for you the bottom and top cross section. So you have everything needed for this part. So you can close this. Of course, you want to save the work you did. Save geometry, geom, test. Okay, close it. Now import your Q data. Q data, you can see at the same time, you can have different numbers of CFS run. Let's leave it as 1, and 10 CFS is good. So I'm applying data. So 10 CFS is what I want to run. You see the unit here is shown as CFS, but you need to define your boundary condition. The upstream, you can leave it, but for downstream, you need to have 1. So let's say I want to run for a normal depth with the slope of 1%, and apply and save. So that's my flow test. And now I want to save this. Now I have everything. I don't have a plan. So the plan, when you click on run steady. So run unsteady and everything is advanced, but run steady. So basically you can have an ID, just TT, and then that's good. You have a geometry, just 1 version of it. You have flow, 1 version of it. You just want to run it in a subcritical mode to see what happens. And run, boom. So congrats on your first successful HECRAS run. So you want to see your results now, your results, cross section. So basically it's showing you, you have half a foot, your bottom elevation is 7, so 0.49, you have half a foot of water in your downstream cross section. Let me move to upstream one. Again, you have half a foot, which is 0.49 foot of water in your upstream. So basically this is a uniform flow. I am showing you the cross section. So let me now show you the profile, so that makes sense to you why I'm saying this is a uniform flow. This is a very uniform flow. And the profile view can show you basically you are at normal depth, which is also your critical depth. This red dashed line is the critical depth, which is happening exact same elevation as the water. And then green line is your energy grade line. So water surface plus the velocity head. Very helpful information so far. You can make this a 3D. Here, the 3D, there is a 3D view. So just say yes. And now you can see this is your channel, very uniform. And of course, you can make all useful tables, energy, grade elevation, energy slope, everything, wetted parameter, everything you have learned in this course. Basically, CFS is 10. and also this big table showing you numbers for each cross section. Fluid numbers is around 1, is exactly 1 actually. That's meaning your flow is running as a critical flow. But is that the case always? No, in this particular condition, because I have a rather steep slope, it's happening to be a critical depth. So now I want to change it to show you that's not always the case. If you make the slope milder, I want to make this slope very mild at the boundary condition, and save and run. So let's see. When I make it mild, then my cross section, now in the downstream one, I have around 2 feet of water, but at upstream, it's half a foot. So this is not critical anymore. The profile view shows me it's not critical at all. Towards the end, you can see water surface is touching the energy grade line. Basically, that means you have a very, very slow velocity here. Because the slope is super mild, it makes the water to slow down almost still. And you can see your critical depth is going to be half a foot of depth, but your water flow is not following that. That's a very, very interesting thing to show with HECRAS. You can test all things. You don't need the actual physical flume. You can test many things. You can run many numbers for CFS at the same time in the model. And of course, if you want to see it in the 3D mode, then you can see, again, it's not uniform. It's increasing depth towards downstream. And to tables, of course, your velocity is dropping a lot. You start with something or near the critical flow, but towards downstream is very subcritical. That's a change you can do, and you can study with HECRAS. You can make other changes. You can have now maybe 2 different values for Q running at the same time. So I'm changing this to 2, and then that gives me another column. So now I want to run it with 50 CFS at the same time and apply it. And then, of course, you run, and it runs both for 10 and CFS combined. So your figure is going to be busier if I show this plot. So of course you need to bring in the profile. So I click both, and so let me get rid of one. Okay, so for number 2, it's going to be basically kind of flat water surface, and I want to show it in this mode again. It's basically lots and lots of water, so we're not showing it in the, so the water is basically in the upstream situation. It's okay, makes sense. It leaving the main channel, going a little bit towards the overbanks, but at downstream is fully flooded. You can see it's even higher than the depth that I had for my overbank. So that's basically lots of water you have in this tiny channel. So if you're designing something for this, then your bottom width of 5 foot is not helping you. You need to make it 10. You need to make changes. That's how you design things with HECRAS. And that's it for basically how to do your first HECRAS model. Basically save and geometry and flow for steady. If you want to do unsteady, quasi-steady, these are your options. If you run or sediment or water quality, that's your options. And of course, this is run for steady. Of course, you have run for unsteady, sediment, water quality, and everything. This is the window that takes you to the GIS world. So you can incorporate GIS data in your model. So that makes the process of creating cross sections a lot easier. And there, everything else is for understanding the results. So I hope you enjoyed this elementary first step video to HECRAS, and we will have you for more videos on this topic.